Thank you guys for being here today for this periodic seminar. This will be the last seminar before the Christmas break. So I hope you enjoy all the seminars that have been done so far, and that this one will be also, that you will also enjoy this one by António Barros on real-time scheduling of STM transactions on multi-core platforms. You have around 45 minutes. So,
thank you, Patrick. Let's start. Okay, this is the problem in which most of us are working in some aspect. Previously, we had a computer architecture for real-time systems that consisted on a single processing core, a single bank of memory, and a single memory bus. The functionality of an application would be divided into tasks, and such tasks would execute on that core, dividing the time. And each task would have its slot to execute on the core. While it was executing on the core, it had exclusive access to the core, exclusive access to the memory bus, and exclusive access to the memory and devices. But we had a well-understood theory and practice on unicore problems. But things were not quite as easy when we changed to the multi-core paradigm. Now you do not, you still divide the functionality of the application into tasks, but now you have several processing cores in which you can execute each task. Mapping tasks to cores is already a large problem, right? But still we have many cores, one memory bank, one memory bus in many architectures. So current and future embedded architectures, we will have multiple cores ranging from tens to hundreds and probably thousands. Probably no cache coherency, because it's very hard to keep coherency of caches when you are scaling to hundreds of cores. And most probably one memory bus that is being shared by all these cores. So maybe this is okay for sets of independent tasks, that basic abstraction when we start thinking about real-time systems. But what if tasks are not independent? If they share data, if they share devices, and even if we think about traditional independent tasks that were not sharing data and not sharing devices, currently they are sharing the memory bus, right? So we have this problem in which we have a bottleneck in the memory access. Are independent tasks really independent? Let's have a practical case in avionics. We have a new programming paradigm which enhances the explicit dependencies between functionalities. It is required to have spatial and temporal isolation among functionalities, depending on their criticality. And functionalities must be statically assigned to cores. And of course, data dependencies must be met, so we know which kind of dependencies we have between tasks. I think the batteries are being depleted. So there are some previous attempted solutions, like the flexible multiprocessor locking protocol, FMLP, in which global resources can be short or long. What is this short or long? It depends on the time that you require to execute this critical section. Short or long is a term that is chosen by the designer, so there is no mathematical law to say this task, this critical section is short or long. When a critical section is blocked, it busy waits on short, if it's a short critical section, or it suspends if it's waiting for a long critical section. And there you have a problem-solving mechanism in which requests dictate joining resources into resource groups. If you have two critical sections that require one resource, this resource forms one group, and both tasks belong to that group. But where does the group come from? If you have, for instance, let's say that task 1 requires resource A, and task 2 requires resource A and resource B, and task 3 requires resource B. Since task 2 requires A and B, this is grouped into one group. And if resource B is being requested by task 3, task 1 cannot access task A because there is one single lock. Controlling the access to the resources inside this resource. So FMLP tries to keep the granularity of contention as fine as possible, but in the extreme you can have one single group containing all the resources. If there is lots of tasks requesting just this, and then the other one requires this and this, in the end you may have one single coarse lock. Critical section code is executed non-preemptively. This is such that a lock can be, once it is acquired, it can be released as soon as possible. Of course, this has the problem of this big group lock. I don't know if you are following me or have any questions. Okay, so attempted solutions. Our idea is to use software transactional memory, which is a concept that is not mine. It's a concept that comes from the 90s, and it gained some momentum in the middle of the 2000 decade with the multi-core. Once the multi-core became established. And we have SRPTM, which is one scheduling extension that we are proposing. Okay, in here there are no groups and no locks, at least as seen by the programmer. So each transaction that is somehow equivalent to the critical section just knows which objects or which resources it needs to access. So they don't need to know which group or whatever. I just need this data and this data. And contention is checked at runtime, just in time parallelism. So at any time, for instance, if T1 requires A and if T3 requires B, once they try to update the values, there is an underlying mechanism that will check if it's okay for T1 to update A and T3 to update B. Okay? So you can have this higher, finer granularity in time. But we have to upper bound atomic section response time because software transactional memory relies on the possibility of aborting a transaction and then repeat it again, which is something that is not the case in critical section. In critical sections, once you have a lock, you can execute and you are sure that in the end your updates will be committed, right? Because you have done in mutual exclusion. With transactions, everything goes in parallel. And in the end, you'll check if your updates are valid or not. And if they are not, okay, just dump your work and do it again. This has, of course, an obvious impact on the execution time of tasks. And we must upper bound the atomic section response time. And of course, since we can abort and retry, blocking times can also increase. And we must limit this blocking time, so we will not have indefinite, not to say infinite, blocking times. Is it okay? Is it clear? Mm-hmm. Okay. Background. Coarse-grained locking. In coarse-grained locking, you have, for instance, this memory locations. I believe there are 6. Yes, there are 6. And you have one single lock managing the access to several of these memory locations. If you have, for instance, task 1 that requires to write in position A, it must get or acquire lock 1 before do the write operation and then release lock 1. We have here a second task, task 2, that requires to write on position on memory on object C, and it must get the ownership of the same lock. So, although they are accessing different memory locations, in the end, they have to they have a problem here that is they are getting the same, they are acquiring the same lock. So task 2 cannot get this lock before task 1 releases it. So although this could be 2 operations that could proceed in parallel, they cannot. They have to be serialized, which is not nice. Let's say. So critical sections cannot progress in parallel. I'm sorry. It's easy to rewind, but it's not that easy to fast forward, or there is no fast forward.
Especially not in life.
Yeah. So, on the other side, we have fine-grained blocking, in which you have locks, but each lock controls not so many data locations. Probably you can group some, but you have one lock per 1, 2, 3 memory locations. This provides much more parallelism between applications. For instance, we have here 2 tasks. The first task needs to read object C and write object A. This one reads object B and writes in object C. And since this one needs to okay, C and A, it requires lock 1 and lock. Oh man, I have here. It should be here too, right? Okay. It needs to get the ownership of locks 1 and 2, and here it requires to get the 1 and 2 again. I think that I wrote the tasks and then I changed the drawing probably, or maybe I was too sleepy when I did this. Sorry. But we have here the typical case of a deadlock. Locks are not acquired in a predetermined sequence, and tasks can deadlock because this one gets lock 1, this one gets lock 3 at the same time, and when this tries to get lock 3, it suspends because lock 3 is already owned, and the same happens with this one when it tries to get lock 1. Okay, so fine-grained locking brings the problem of possible deadlocks. So you need to know what is the correct sequence to acquire the locks. The programmer must know the correct sequence to acquire the locks. And otherwise you have the possibility of having deadlocks. And the problem of having locks is also that the programmer must know which lock controls which resource. So if you have many resources and many locks, you will need an extensive documentation saying that this resource is owned by this lock, this resource by this lock. And in fact, you will get a programmer's hell. So fine-grained locking increases system complexity with a negative impact on composability and maintainability. Right? Whenever you want to change an application that is already in mission, you have to check the documentation of resources and locks and see if there is if this modification will have an impact on other tasks. It's madness. Or nightmare. Okay, software transactional memory is a different approach in which you have a system that manages the access to the memory positions. And you have tasks that say, I'm entering a transaction, and in this transaction I have to, for instance, update position A, and this one is updating position C, for instance, in this example. And in the end of the transaction, the task will try to commit the updates. Okay? When it tries to commit, the thing is that it will ask, okay, you have task 1 and task 2. This is the part of the animations that I sometimes forget, but they are cute. You have both tasks. Once they start the transaction, both tasks are active, and when they try to commit, the software transactional memory checks which objects are being accessed, and it will decide if the transactions are valid and will successfully finish, or if there is one conflict that must be solved. For instance, here it checks that there is a write on object A and a write on object C. There is no conflict, so both tasks, both transactions are allowed to commit, and from active they will finish, and it's done. Another example in which we have also two transactions, but here we have conflicting accesses. Both are trying to write on object E. So you have task 1 that starts first. You have then task 2 that starts right immediately. And when they both try to commit, let's say that they try to commit at the same time, the software transactional memory system checks the accesses and detects a conflict. So what does it do? The system says, okay, it's all right for this task to commit, and it's done. But since this task has since this transaction has committed, the other one cannot commit because the validity of the data is now false. It's not valid, and so task 2 goes to a zombie state in which the data is not valid, and then it will eventually fail and will have to restart. Once it restarts, does the same, executes the same code again, no conflict, okay, and it finishes. Right? Problem. Any problem? No?
How do you manage the order?
There is a full book of recipes, and I will show a few recipes in one of the following slides. So, managing contention. Here are some of the recipes that I was telling you. You didn't need to wait too long. Okay, we have the polite, in which when a transaction checks that is trying to access an object that is already being accessed by another transaction, it exponentially backoffs, so it gives some time for the other transaction to finish the execution and possibly commit before trying again to access this data. Eventually it will commit, except if the data becomes invalid for itself. We have here an aggressive in which a transaction checks that this object is already being accessed by another transaction, so kill it. I have the priority. That's like this. Kill the enemy. We have the randomized in which you throw the dice and with some probability you will wait, or with the complementary probability you just abort and restart again, and probably the next time everything will be okay. Timestamp. The older transaction survives. This one requires that the software transactional memory system records the timestamps at which each transaction starts, and the oldest one in the system is the one that will prevail. This is a nice approach because it provides all the transactions the opportunity to finish along the time. And we also have the karma that prioritizes the one that has performed more work. So the hardest worker transaction is the one that will prevail. How does it account the work? It simply counts the number of objects that were already accessed, and also how many times the transaction was aborted. So this raises a value that is called the karma, and the one with the highest karma is the one that will commit next. So all the transactions will have the opportunity to build muscle, and when they are like this, they will commit. Eruption. This is one that is similar to karma. It's like once you wait for another transaction you give time to another transaction to do their work, you start gaining some value. And in the end, once you have all this value, you erupt and you will be for sure allowed to commit. Okay, From all these recipes, the one that is purely deterministic is the timestamp. Once you start a transaction, you know which transactions will commit before you, and you know which transactions, the one that will come later, will not be allowed to commit before you. All the other recipes are non-deterministic. For instance, the polite, you know that is not very deterministic when you want to enter a lift and you say, oh, please go, you can enter, and the other person says, no, you can enter, no, you can enter. You can stay the whole life waiting for the other one to enter. So it needs someone to say, okay, I will enter. Okay.
But you are you are assuming static analysis, or this happens during runtime?
I don't get your question, but this is
You are saying that.
this is performed in runtime.
Okay.
All these recipes.
Okay.
But nevertheless, all these recipes come from the parallel computing. Like,
how do you know what transactions come? So if you have a transaction that is going on, how do you know the transaction that will come in the future?
you don't know.
You don't know. Okay.
You don't know.
You only know the transactions that are occurring at the same time. I mean, the ones that are waiting. to
Yes.
complete. Okay.
Yeah. And this comes from the parallel computing, not from the current one, but from the old ones, in which you have massive data, and then you have a computer with a massive number of processors. You divide the data, and then you have parts of the you have the same routine working on parts of the. And their major concern was that they wanted the results as soon as possible, but not within a deadline. Well, as long as if you are still alive when you get the results, it's okay for them. And so they didn't have these strict timing requirements as we have in real time. And most of these decisions were done immediately when they were checking, where they're trying to access the data. And when they were doing this, most of the time they were just checking for update operations, like conflicting writes and writes. And if you were doing a read, reads were mostly invisible, so you could be allowed to write without caring how many other parallel tasks were reading the same value and could be invalidated by this update. This is something that is also bad for real time, because we could be invalidating transactions that were being carried by higher priority tasks. I don't know if you followed me now. The thing, so we also have to change a little bit this paradigm. Let me see if I talk about this in the future slides. If not, I will do a lateral explanation. So, model of computation, and we have multi-core computing architecture with a single memory bus. Our work is assuming this computation platform, and data is shared in global accessed memory controlled by an STM system. So you have one global memory. All tasks can access the same memory, right? But once a task is executing in a core, it has its own copy of the data set. Okay? So it can proceed in parallel and fast, instead of having all these collisions trying to. So Okay, application characteristics. Functionalities are divided into tasks. Each task releases a potentially infinite number of jobs. This is not new for most of us, I believe. A task has an execution time, a period, and a deadline. And a job has a release time and an absolute deadline. And each task is statically assigned to a core before runtime. So we are assuming a partitioned approach. Once a task is dedicated, is assigned to a core, there is no way to move this task to another core. Okay, maybe I can move on. So this is the task. The task is the set of these issued jobs. You have here the release time of this job. You have here the execution time of this job. Once it is released, it has this deadline, so it must finish before this time instant, and jobs are released with this period. Serialization of transactions in a real-time environment. Okay. First in, first out serialization of transactions. This solves us the problem in a predictable and fair way, right? As we saw in the previous recipe, once a transaction has a timestamp, this transaction knows that will finish once all the earlier transactions are done. But maybe the problem is not solved, because what happens when jobs can be preempted while executing a transaction? And what if multiple transactions can be simultaneously in progress on the same core? Let's look at an example. For instance, let's assume that we have two tasks executing in two cores. You have here this task. This task starts to execute this transaction that is painted in green, and we have this task on core 2 that starts executing this task here. This task starts later, but tries to access and update the same memory location. Since this one is the earliest transaction in the system, when it tries to commit around here, it is allowed to commit. That's why it's painted in green. It was allowed to commit, so it finishes. But at the same time, invalidates this transaction. So this transaction probably will continue to execute, but it's not already active, it's zombie. When it tries to commit, it asks, can I commit? And the STM system says, no, you are a zombie, so restart again. And it will restart. Okay, no conflict now, and it is allowed to commit. That's why it's painted in green. But now we have, at this moment, it's the same set of tasks, but now we have here another task that is more urgent, that arrives at this point and will preempt this task while it was executing a transaction. What is the consequence of this preemption here on this task? We don't know. We have one situation here. And what if this task also starts executing a transaction here that tries to access the same popular object A? Everybody wants to access object A. What will happen here? Oh, in the previous one, this one should commit here, or wait for this one to finish. And here in this situation, what happens here? Which one will commit? If this one is waiting for this one to commit, and this one is waiting for this one to commit, we have here a deadlock, which is something that we thought it was not possible with software transactional memory. Right? We have here a circular dependency chain, and we have a deadlock.
So you are not assuming that memory accesses are not non-preemptive? Because previously you were saying that memory accesses were non-preemptive, but now you are not assuming that in this particular case.
Memory accesses were not preemptive on FMLP.
Ah, okay.
Critical sections are not non-preemptive.
So for now you are assuming that they, okay.
The source of the problem here is that for the parallel programming guys with massive data, they don't preempt tasks. Mm-hmm. You have here a thread task executing on this core, and probably it will execute in exclusive. It will not be preempted. But when we have these situations in which you have tasks that can be preempted by another task that will execute a conflicting transaction, you can have deadlocks here. So, in situation one, we can increase what to do. For situation one, we can increase the resistance to preemptions if a transaction can affect concurrent parallel transactions in jobs while meeting all timing requirements. Okay, it's like this. If I'm doing, sometimes I need to think about what I wrote, what I meant to say. The thing is like, I'm executing a transaction, so probably I should resist to be preempted because other transactions in other cores may be waiting for me, maybe waiting for me to complete, so they can proceed, right? So increasing the resistance to preemptions, it's probably a good idea. No, not a good idea. Okay, I can.
Can't you use something like priority ceiling or priority inheritance protocol and apply this to this kind of thing?
I use something similar. Okay. I use something that was based from the stack resource protocol.
Okay.
So what I was saying is that this transaction should increase the resistance to be preempted because other transactions in other cores could be waiting for it to continue. And if I finish this as soon as possible, I'm sure that these transactions will also finish as soon as possible. And in situation 2, restrict to at most one transaction in progress per core. This avoids deadlocks, and we assume that in order to avoid deadlock, we will not transgress the first in, first out serialization. Why is that? I will use the whiteboard because it's easier than rewinding the presentation. It's like I'm doing here a transaction, but all of a sudden it is preempted by this one that executes a conflicting transaction. So let's say that this one is write A, and this one also writes A. If we don't want to have a deadlock situation here, what we must do is to allow this transaction to commit before this transaction that is older, right? But if we allow that, we are already transgressing our rule of having these transactions serialized by their order of arrival. Okay? So if we do not allow this transaction to start, here we can complete, and then we start here, and transactions continue to commit by their order of arrival. Okay?
Silly question. But in that case, you don't need transaction. Because you are actually serializing the access to memory. Why do you need a transaction in that case?
We have to.
Just because you want to control.
You have
Because it's the same thing as serializing memory accesses.
You have to serialize memory accesses, because otherwise you will have invalid data right very, very shortly. That's the purpose of critical sections or atomic sections. I access this set of data like if no one else in the universe accesses it while I'm accessing it.
Well, I got that, but what I'm saying is that you don't need the burden of software transactional memory for that. Because if you are serializing the accesses, you don't need to...
You are thinking in one core. But if you think in two cores, you can have transactions in parallel. And software transactional memory, what it does is to check if these two transactions, three transactions, 100 transactions that are proceeding in parallel, which ones can commit in the end and which others don't commit.
Okay, but those mechanisms only work for one core. Okay, I got.
This rule is for each core.
Okay.
On each core, I will not allow more than one transaction at any given time. Right? And this is the basis of SRP-TM. SRP because you'll see it's based on the stack resource protocol, TM, transactional memory access. So, scheduling jobs with transactions on the SRP-TM way. General scheduling rule, partitioned in the F. So, tasks are generally, in our approach, they are generally scheduled by the partitions in the EDF way. But once a transaction starts on a core, we slightly change the EDF algorithm into the extension SRP-TM, in which we add static permissions, static preemption levels to tasks. We also add static preemption levels to transactions, and we add also a variable core ceiling. This is similar to stack resource protocol, and this is also based from the stack resource protocol. And I think that this one also, there is the task level, the core ceiling, and I'm thinking if there was the critical section. You can cut this from the video, right? It's not nice to show my doubts here now. Okay. So the highest preemption level of a task that could be waiting for the current transaction in progress to commit. This is what means the course ceiling. Let's look at an example. How do I assign preemption levels to tasks? Okay, just like in the stack resource protocol, we assign preemption levels to all tasks by their increasing order of relative deadline. So the ones that have higher relative deadline will have the lowest preemption levels. So it's like setting a number on the emergency or urgency of the task. The shorter the relative deadline, the higher the preemption level. And we do this independently of core affinities. So we take the task set as a whole, and we don't care to which cores tasks will be mapped. And now, for instance, here we have tasks 7 and 6 that have the same relative deadline, and we give the same preemption level. So when I did this, I found this interesting. Now I think it's pretty obvious, probably. Okay, and then assigning preemption levels to transactions. Okay, to assign a preemption level to a transaction, we must check which is the highest preemption level from all the tasks that have a transaction that may have to wait for our transaction, our object of analysis sorry, I need to start the sentence from the beginning. How do we assign a preemption level to a transaction? It's the highest preemption level from a task that has a transaction that could be waiting for our transaction to complete so it can proceed. For instance, we have here 3 tasks, one at core 1, this one is assigned to core 2, and this one is assigned to core 3. Their data sets, this one accesses object A, this one accesses object A and B, and this one accesses only object B. And this is the first transaction to start, so it will commit in the end. This one starts afterwards, so as they are simultaneously in time, this one will have to wait for this one to commit before being able to commit. So once this is ready, this one is free to commit, and it will commit in this attempt. It looks a little bit different than the previous slides, but the notation is the same. Red aborts, green commits. And this one that starts, that is the latest one to start, will have to wait for this one to commit. So only here it is allowed to commit. Here it becomes a zombie, and then this one will succeed. This one will have to wait for this one, and indirectly will wait for this one to commit. Right? Because if transaction 3 is waiting for this one to finish, and this one is waiting for transaction 1 to finish, it is directly waiting for this one, and indirectly waiting for this one to commit. Right? Seems logical? So, we have here a contention group. Although this is not a direct contender with this one, in fact, it waits for this one to finish. The amount of time that requires to commit is affected by the time that this one needs to commit. This is a very small example in which you have 3 transactions in 3 cores, but you can think of a chain of n tasks and transactions in n cores, right? In which this is waiting for the direct contender, that is in turn waiting for direct contender. So this one has indirect contenders that must wait for. Okay? So, where do I want to reach? You have here transaction 1 that shares the access to object A in their data set with transaction 2. Transaction 2 shares this interest in object B with transaction 3, and these transactions form a contention group. Here I'm mapping the data dependencies between tasks or transactions. These are transactions, and these edges represent the shared data. All transactions that are connected form a contention group, right? Which means that if you have, for instance, a job of transaction T1 that is not very urgent, it has a far deadline or a low preemption, a low priority, probably it could be preempted several times during the transaction. And you could have a high priority job here that was waiting already, that is waiting for this one to commit. So when we assign priority levels, preemption levels to transactions, we should think about the highest priority of the transactions that could be waiting for this one to commit, right? It may not be this one. It may be an indirect contender. Practical example, we have here 2 contention groups. We have transaction 1 and transaction 5. They share the same interest on object C, and we have here transactions 2, 3, and 4. They share their interest on objects A and B. This is the timing, this is the relative deadlines of the host jobs. For instance, this one has a relative deadline of 50 time units, and this one has a relative deadline of 120. If we assign the task preemption levels, you would have, for instance, this is the lowest one because it has the largest deadline, 1 and 1. This is the task preemption level, and this is the transaction preemption level. So this is 1, and this is the most urgent. It will have the highest preemption levels, right? But since, okay, this is the legend that I just, but since this transaction may have to wait for this transaction to commit, the preemption level of this transaction is raised to the task preemption level of this one. Yes?
But in that case, the deadline is earlier than the other one. Why do you need to have that difference?
Sorry?
In that case, W1 or omega 1
Yeah.
finishes earlier than, I mean, it has a higher priority than omega 5.
Yes.
So why do you need to have, even though they depend, I mean, they
It's
write-
executing on another core.
Okay. Okay.
For instance, we have here which one is the here is task 5 executing omega 5. And here you have in a different core task 1 that is executing omega 1. And since this one in this core has a far deadline, it could be preempted lots of times. And it was only allowed to finish here, which was past the deadline of this one. So what I do is, while this task is executing the transaction, it will have the preemption level of this task. Okay? So it's like if momentarily it has this deadline. Not rigorously speaking, but so transaction versus transactionless. If you have on the same core a job that is executing a transaction, if you have a more urgent job arriving, it will preempt, and then once it finishes, this one finishes the transaction, and I think I probably skipped one slide maybe. There were a set of rules, extra rules, that I don't remember, I talked about them. Okay, but doesn't have a transaction, it's okay, it is allowed to preempt as long as it has a higher preemption level than the transaction that is being executed. But, for instance, in SRPTM, that was on pure PEDF. PEDF doesn't care if it's executing a transaction or not, just preempt. I forgot to read the small letters there. But here on SRPTM, this is only possible if the task preemption level is higher than the transaction preemption level. Okay? And this is the core ceiling. It was 0, but once it started here executing the transaction, it was raised to 6. And here we have also a more urgent job that arrives, but it doesn't have enough preemption level to preempt the transaction. So here the transaction finishes, and only when it finishes, this job is allowed to preempt the job. Okay? So here the transaction was saved from being preempted. Because probably there is a more urgent job expecting this transaction to finish. This is direct blocking, because it's waiting for a job with not earlier deadline to execute. Okay, transaction versus transaction. In PDF, all jobs are allowed to preempt lower priority jobs, so you can have here a transaction executing while the other transaction was preempted. On SRPTM, we do not allow that. So even though this one has a higher preemption level than the transaction that was already executing, it will have to wait for this transaction to finish. But in order to prevent that this transaction is preempted by an intermediate job without transactions, what we do is when this tries to execute the transaction, it raises the core level for its own core level, its own preemption level, sorry. Okay? And once it finishes, the core ceiling goes to 0, and when it starts the transaction, it is raised to 8. Here it should be also an 8, sorry. So we have the direct blocking and mixing all together with jobs with transactions and jobs without transactions. Here you can have any sort of preemption pattern, but when you have SRPTM, this one is allowed to preempt this one because it has higher preemption level. But when this one arrives, and this one has the highest preemption level of all, it cannot execute because it has a transaction. So what does it does? It puts it raises the core ceiling to its own preemption level and says the scheduler finish the other transaction as soon as possible. And this one is scheduled. Once it is finished, PDF says that this one is the one that should execute, roll, and then we have the natural flow of things. Here we have direct blocking and here we have indirect blocking. Because here it is waiting for this one because it's waiting for this one. Okay. I think I should move this set of rules to an earlier part of the presentation. Response time of a transaction. I will have to skip, sorry. I have the conclusions summarizing what we have here, but it is hard. The main thing is that it's very hard to calculate the response time of a transaction, especially because we have these trees of contention. You are not just waiting for the direct contenders to finish. You may be waiting for the indirect contenders to finish. So finally, our direct contender will commit and it's done. The problem is combinatorial. Yeah. So you can have many ways in which transactions can interfere. You can have many paths until of transactions before this one commits. If you want to derive a response time, you must go to more pessimistic approaches like, okay, for each core, which is the longest transaction, and use this value, which is very fast to compute, but it gives you an error margin. Like you can see here, you have here an upper bound, and you have here the actual response time, so you have here an error. The response time of the last two transactions, the one direct, can be analytically upper bounded, but to determine every possible sequence, it's a combinational order problem. I'm already exceeding a lot the time. Simulation results, we have simulated with pure partition DDF, non-preemptive until commit and non-preemptive during attempts. These are non-preemptive ways of scheduling tasks that we first derived. Here it is just simply saying 2 more minutes. In non-preemptive until commit, once a transaction starts until the transaction commits, there is no way to remove the task from the core. So there is no way to have preemptions. Here in NPDA, non-preemptive during attempt, you have preemption points every time a transaction fails to commit and before retry again. So the scheduler has the opportunity to check if there are more urgent tasks here at this time, and it will schedule those more urgent tasks before retrying the transaction, which gives you more flexibility, more responsiveness to higher priority tasks. This is the one that we talked about here, and this is FMLP, the locking approach. We did 2 experiments, one varying the system size and another one varying the size of contention groups. And the results, okay, we put a heavy burden on the task sets that we used, and PDF had the highest feasibility rates, but when you started increasing the contention, it dropped, and the ones that have better or less bad performances were NPDA, and it's hidden here, SRPTM. When we limited the size of the transactions, like, okay, we have small transactions, things improved, but still PDF, since it is the more not flexible, but the more flexible way to schedule tasks, it had the best results in the beginning, but once the contention started growing, this is always like the contention growing on here. It would go down. Everything goes down, but NPDA and SRPTM in some cases were able to feasibly schedule more task sets. Missed deadlines. We accounted the number of deadlines that were missed on the task sets that were not feasible. And FMLP, the locking protocol, was the champion of missing deadlines. So, because it was too strict. On the other side, SRPTM was the one that was missing less deadlines. Here, when we were changing the number of, contention groups, we also see that SRPTM constantly shows the best results. So for soft real-time tasks, SRPTM proves to be better than other approaches. And the locking approach is always the worst. The time required, the overhead time that was produced by abort and retry on the STM approaches and on spin locking on FMLP was also counted, and SRPTM is the one that has less overhead. It's the one that misses, that spends less time aborting and retrying, while the locks here simply explodes. FMLP, whoa. When the contention grows, the amount of time waiting, spin locking, goes sky high. Wrapping up, first in, first out serialization is predictable and fair. Scheduling has an effect on the performance of transactions, especially preemptions. And SRPTM extends PDF when a transaction is in progress on a core. It takes into account possible concurrent parallel transactions with earlier deadlines without sharing scheduling data between cores. This is something that we also wanted because we didn't want to exchange data between schedulers to check, is it okay, what's happening in the other cores? This thing is simply impractical when we have hundreds of cores. We don't want to have hundreds of schedulers sharing data saying, I'm not scheduling this particular type of task. So, and it allows jobs with earlier deadlines to preempt or speed up a transaction in progress. We provide an analytical method that I've even discussed here because of lack of time to upper-bound the response time of transactions under SRPTM, and we also provide an analytical method to upper-bound the response time of tasks under SRPTM. And thank you. Is there any more questions?